Good morning to all dignitaries. I am M. Madhubabu, research scholar under Professor K. JNT University. I am here to represent our research work, and its title is Optimal Utilization of Hardware for Real Valued FFT Architectures. Our objective is to implement the real valued serial commutator FFT architecture using reversible logic gates, and to reduce power consumption and die area by replacing irreversible logic gates with reversible logic gates in FFT architecture. The contents will be like this. The presentation contents will be like this: introduction, existing work, FFT implementation using reversible logic gates, tools used, power and area analysis, applications, conclusion, and references. Coming to introduction, there are various types of pipeline FFT architectures already implemented. They include serial and parallel pipeline architectures. But there is inefficiency of hardware when we are dealing with serial architectures, as serial architectures need n number of cycles if you are dealing with n-point FFT architecture. But butterflies work with n by 2 cycles for n-point FFT. So butterflies are only used half time, so hardware utilization is 50%. So this is a simple introduction to basic butterfly operation in serial, pipelined serial architecture. So the existing work is, in this existing work, they deal with real valued serial commutator FFT architecture. This FFT deals with real signals where the input is processed in serial manner. So this architecture, this existing work, achieves utilization hardware where each stage of FFT is mapped to half butterfly operations when compared to full butterfly operations. So these half butterfly operations use one adder per stage in FFT architectures. So the same existing work we are using, and we are replacing irreversible logic gates with reversible logic gates, and how best we can reduce power and area by replacing irreversible logic gates with reversible logic gate techniques. This is basic 16-point decimation in frequency FFT flow graph, where the dotted, the colored portion can be removed because of symmetric property of FFTs. So in order to understand the symmetric property of FFTs, so equation 3 deals with symmetric property of FFTs. X of n minus k is equals to x convolution of k. So equation 1 is a typical operation of butterfly. In typical operation of butterfly, we need 2 rotors and 1 adder or subtractor. By modifying it in equation 2, we need only 1 rotor operation and 1 butterfly operation. So in order to reduce area and power, the utilization of hardware component should be reduced. So equation 2 satisfies our requirement, and equation 3 reduces the number of operations because of symmetric property. So by using all those in mind, the FFT 16-point DFT FFT flow graph is reduced to like this. Just see here, this FFT flow graph is reduced like this. So we try to implement this by using architecture. This is the 16-point real valued serial commutator architecture. So in this, we use a real valued structure, PE1, PE2, PE3, and PE4. All these architectures, all these butterflies are implemented separately. This is the first butterfly in first stage 1, PE1. So if you see this, whatever input you give, that particular input is controlled by a selection line, and depends on the selection line whether if selection line is 0, you will perform addition operation, or if the selection line is 1, you will perform subtraction operation. Excuse me. So this is the timing diagram of this particular butterfly. At t0 time second, we are giving x1. At t1, x9. At t2 time second, we are giving x5. At t3 time second, we are giving x13. At t4 time second, we are giving x3. It's a random number representations. So at t0 time second, if you give x1, the value of m will be assigned x1 only at t1 time second, and the value of n1 is assigned only at t2 time second. So x in and xn has a time delay of 2, x in and m has a time delay of. By defining all those things, we deduce the results with respect to selection lines. If selection line is 0, we get addition. If selection line is 1, we perform subtraction. It depends on that. Everything will be operated in basic butterfly of stage 1. So the same butterfly operation we modified to get all the different butterfly operations in all the 4 stages. This is an extension of this, adding another selection line, which is used as a alternative butterfly for all the 3 stages. And the first stage will be the same butterfly operation. And this is a 3-stage rotor inbuilt in butterfly operation. All these rotor and butterflies will reduce in the effective implementation of FFT operation. But implementing all these butterflies, we are using Fermi gate and Peirce gate. Fermi gate and Peirce gate are reversible logic gates, and their inputs are A and B. Output will be P and Q. P will be equals to A and Q will be equals to X, J XOR of P. And the Peirce gate input is A, B, C, and the outputs are P, Q, and R. P is equal to A, Q is equal to A XOR of P, R is equal to AB XOR of C. Depends on the application, depends on the usage of gate. We can either use Fermi gate or Peirce gate or both the gates. Please consider an example of 1-bit adder. It's a combination of Fermi gate and Peirce gates. FG is Fermi gates and PG are Peirce gates. The combination of Fermi gates and Peirce gates with respect to a control pin and inputs A, B, C, we get sum or difference, carry or 1. If control is 0, you get sum and carry. If control is 1, you get difference and 1. So this is the example of reducing reversible logic gates for adder or subtractor of 1 bit. So we implemented all those things by using the cadence tool, RTL's compiler with 90 nanometer technology with a clock frequency of 100 megahertz, and we performed functional and timing verifications in Questasim 64-bit 10.4 edition. All these results are deduced from RTL compiler. The results deals with the power consumptions of irreversible logic gates with respect to reversible logic gates. Irreversible logic gates, leakage power, dynamic power, and total power. reversible logic gates, locus power, dynamic power, and rotor power. When compared to irreversible logic gates, the architecture defined by reversible logic gates is considerably less power consumption. So, in the same way, the area consumption of irreversible logic gates and the reversible logic gates we can observe on the cell standard and semi custom cells count is also displayed. It is 17,607 and 13,006 standard and semi custom cells are used to implement this particular FFT architecture. So when compared to irreversible logic gates, reversible logic gates FFT architecture consumes less area. So these are the simulation results where you get input, multiplication, operation, and output of the resultant FFT architecture. So this is the RTL view deduced from RTL compiler in Cadence environment. So here we are using irreversible, we are replacing irreversible logic gates with reversible logic gates, and we are successfully implemented it, and we also showed that the amount of power consumption and the amount of area reduced with respect to irreversible logic gates. So there are a number of applications of reversible logic gates. The major application is these reversible logic gates can be used in low power applications, any applications. And there are another applications like cryptography, nanotechnology, computer graphics, and optical computing, where irreversible logic gates, FFT applications can be used. This FFT applications can also, the real valued FFT applications can also use it in medical field also. So we are concluding that reversible logic gates, which we use to implement adder and subtractor operations in butterfly operation, reduced considerable amount of power consumption and area by 20% and 17% with respect to the existing system. So replacing irreversible logic gates with reversible logic gates helps us to get that the same operation with the less power consumption and less chip area. In turn, it reduces with less cost, because cost is directly proportional to chip area and timing. So these are the references which we use.